Okay. Good afternoon. So I think it would be better if we don't continue with teaching, but let us try together solve some of the good problems which are mentioned in the book. But please try to communicate with me. Consider this as a review session for what we learned in chapter 4. Yes, that would be good. So, because there was a lot of information that I passed you. So let us just to slow down and try to solve some problems. Okay. I would say that might be it's a good idea if we start with a level 1 problem, and then this is the typical problem I really want you to know. So we want to determine the local extreme points of the following functions. Okay, and then you are supposed to say which one is a minimum, which one is a maximum, or might be they ask you determine the nature of those points. So that's meaning the same thing. So if you don't mind, let us start. Let us start with part B and try to solve the problem for this case. Okay. So I will write it on the board, and then I will ask you questions. Please try to answer me. So because if you answer wrongly, then I know what the problem is and I try to fix it. So this is problem 4115. I would say part C. So a function is given to you, f of x is equal to x to the power of 3 plus 6x squared minus 15x plus 4. And then this is also a good practice. I recommend you to do it. Solve it yourself and try to check it using GeoGebra, because you also need to improve your skills to be able to work with GeoGebra. Or Desmos, I think, because in exam.net I can also give you access to Desmos. I think Desmos is probably also free. You can have it on your phone as well, I think, if you can check it out. And then in exam.net I can give you access to both of them. So if you are more convenient working with GeoGebra, you can work with that. If you're convenient working with Desmos, you can work with that. But I don't know, I don't think Desmos can do calculations. So it's only for graph. Okay. Anyway, so let us try to solve that problem together. So what is the first step I am doing? So you know that if I want to find the local extreme points, I told you that at the level of your lesson, you need to look for those points at which the derivative is 0. And the reason is that because in local maximum and minimum points, we have horizontal tangent lines, but there is only one caveat to that, and that is the terrace point. So you have to be careful about the terrace point as well. Okay, so the first step, if I want to solve the problem, so let me change my color. So I differentiate my function. I think this is very simple for you to differentiate. So 3x squared plus 12x minus 15. This is the first step. The second step, you equate it to 0. Of course, you can do it algorithmically, but I really want you to understand why you put it equal to 0. Even if you don't understand here, you can solve it correctly, but it is not that useful. I want you to understand why we put it equal to 0. So if I put it equal to 0, so this becomes 3x squared plus 12x minus 15 equals to 0. And of course, I don't bother to solve this problem because I can divide everything by 3, making life simpler for myself. So this becomes x squared plus 4x minus 5 equals to 0. And I even don't bother to solve it using PQ ABC formula because in this case, factorization is very simple. Of course, that is up to you. If the factorization is hard for you, you can use PQ or ABC formula. So I need two numbers whose sum is positive 4 and the product is negative 5, yes?
5 and negative 1.
Yes, positive 5 and negative 1. So the product of two numbers is equal to 0 by the zero product rule. Either x is minus 5 or x is 1. Okay, let me just review things. If I ask you what I gained so far, you will tell me that I found the candidates for local extreme points or possibly terrace points. So we don't know which one is yet. So there are two tests. You haven't studied the second test yet, so we have only one test which has the name, the first derivative test. So if you don't mind, let me write first derivative test for short. So I use the first derivative test to determine the nature of these points. The first derivative test is exactly the sign table. Yeah? So I just draw the sign table. We have a convention in the sign table. The first row is x, the second row is the derivative, the third row is f. And then you have to arrange these numbers in ascending order from the smaller one, from the smallest one to the biggest one, so it becomes -5 and 1. And then the derivative is 0 here and there. So don't get confused, because now you have two functions. One is the original function and one is the derivative function. Whenever you want to say something about this line, you have to look at f prime. Whenever you want to write something about this line, you have to look at f. So if I want to put these, if I want to understand these numbers here, I take -5 and put it in the original function. So you can go to a scratch work. So I put -5 here, let me calculate. This becomes what? So f of -5 is equal to this one to power 3, which is -125. This one to power 2 is 25, times that is 150. Yes? And then this one is +75. And then you have +4. So it becomes 204, yes? Is that right? Yes. So it becomes 204. This one and that one becomes 125, plus this one is 200, and then this is 204. Pardon?
Yes, it's 25.
That's correct, yes. Is that wrong?
Yes.
What is that?
Negative.
Ah, yes, this is 25, yes. 104, thank you. Thank you. Now is that correct?
Yes.
Yes. Okay, now I put 1 here, so this is simple. If I put f of 1, the answer becomes 1 plus 6 minus 15 plus 4. What is the answer? -3. Okay, so what happens? I need to determine the signs here. Okay, what is the sign? You choose a random number that's a little bit bad. So what happens? By the way, I can also teach you. I think it doesn't hurt if you learn that one. So this is my derivative. Whenever the derivative is of second order, you can also do it in a different way. So you need to know where the derivative is positive and where the derivative is negative. What type of parabola is that? Because this one is positive, yes? So it is a parabola opening up. On the other hand, I have two roots. So you can go to a scratch work and try to just sketch. You don't need to be precise at all, because that's not your goal. -5 is somewhere here, for example, and then 1 is here. So what you know that this is a parabola which is opening up and going through these points. So what happens? So it becomes something like this. I don't need to be precise about where that is, but that is enough. Then you immediately see that on the other sides of this, meaning smaller than -5 or greater than 1, the graph is above the x-axis. And between -5 and 1, the graph is below the x-axis. So this means definitely, for example, in this case, it motivates me to think in this way because it was hard for me to put -6 there. So then I would say that this is negative. This is positive because here it's up, and then here it's also positive, but in the middle it's negative. Yes?
If we're doing this in a test, could we be this hand wavy or?
Yeah, I can do it. Yes, definitely. And I don't even bother about putting the numbers. As far as I see that they are doing correctly, that's it. Enough. Okay, and then what happens? This is increasing. This is decreasing because it's negative. This is increasing. By the way, I can also teach you a cheating way, which I don't like, because at this level it always works, because you're always working with continuous functions. So it is clear that when I am up there, and then I reach to -3, there is no way for me to go up. So I have to go down. Yes? Is that understandable? So I am at -4. The height of this is 104. Then I want to go to -3. There is no way for me to go up and reach there. And there is no way for me to go up and then come back. Because if this is happening, I have another extreme point up there, but I do not have any extreme points in between. It's cheating. So the logic is to understand the sign to see what is the behavior. Because for discontinuous functions, you have to be careful. A function which is discontinuous can act like this. It can go up here, and then suddenly it starts going up again. But this is neither a minimum nor a maximum, yes?
But isn't this sine table already cheating in the same way? Because this IOA quickly breaks down when the functions aren't continuous, right?
No, no, that's what I'm saying. The first derivative test doesn't break down that much if you do it on each one of these branches. So what I'm saying is that in the case that the function is not continuous, you have some points at which the function is not defined. For example, if you have x minus 1, but this is not a good example, so let me make it 1 over x. If it is 1 over x, then there is a 0 in which this function is not defined. So the table will look like this. For example, -5, of course -5, assume that this is -5, and here is 0, and then you have a discontinuity here. But then the point is that still you need to know, this means this is the discontinuity. It means the branch on the left-hand side is continuous, and the branch on the right-hand side is still continuous. And the logic is again to determine the derivative on the left-hand side and the right-hand side, and to see which direction the function is going up or down. That's also working. So that's why I'm saying, in this case that the function is continuous, you can also cheat in that way. By the way, how should I know that this is increasing? Can you tell me? Why do you think it should go up if you want to use the cheating method? By the way, this kind of cheating is allowed because you're learning deeper things, yes? Why do you think I can predict that from here to here it should be decreasing? Why do you think I can predict it is going up here and up there? Any ideas? Yes?
Those 2 points has to be maximum points, so we know that they are maximum points.
So how do we know? Because we don't have access to the graph yet.
No, but we know from our calculations.
No, but how?
No, sorry.
Yeah, that is not correct. The point is that to look at the extreme points. So it means that if I go very, very much to the right, for example, plus infinity, what do you think will happen for the value of my function when x is very large? What happens? I have some minus sign in between. When I increase the value of x, these two will increase. This is constant. Then this part will decrease. But I hope that you agree with me which one will dominate. The x to the power of 3 is more powerful when it compares to this one. So this is the way that we write it if you want to. This is just all distraction, sorry for that, for a level 1 problem. But if I say this is infinity. If x goes to plus infinity, that is also plus infinity. Yes? And if I say what is the limit of f of x when x goes to negative infinity, then it becomes a negatively large number. This becomes a positively large number, but compared to these, this dominates. This is a theorem in mathematics. If you have a higher power, that will dominate in a polynomial. So it means that if you want to see what will happen to my function for extremely negative large values, you can ignore all these terms and then think that this is the only term involved. And put a very, very big negative number here, f becomes a very, very big negative number, so it means this limit is minus infinity. So I added with a different color here. This is not what you need to do, but this means that if this is minus infinity, this turns out to be minus infinity, and if this is positive infinity, this turns out to be positive infinity. Now I am at minus infinity, I am in the hell, then I want to reach to 104, so that I have to increase. This means the function is increasing. And then here, I am at minus 3, then I want to go up. There is no way for me unless that I increase the function. So that is the cheating way. I mean, this is a good way of cheating because you're learning more things, yes? But anyway, let me not distract you. The way that I did it when I was teaching, I told you that pick a random number here, which is minus 6, and then be patient and put it here, to put it in the derivative, by the way. You have to put it in the derivative, it is not that big, yes? Because you see, whenever you want to answer these questions, you need to look at this function. I put minus 6 here, you calculate, then you see that you get a positive value, so you put positive here. Between minus 5 and 1, for example, the best choice is 0. I take 0 and put it in the derivative. This one is vanishes, this one is vanished, minus 15. Minus 15 is negative, so it is negative. And then you put a number greater than 2, 1, for example, 2, and then you see that's positive. This is the way that I told you when I was teaching. The one that I just told you, this is up to you. If you want that, it's also okay for me. Especially drawing a diagram for yourself to see which one is which. Any questions so far? Okay, the last thing is to locate which one is maximum, which one is minimum. You see that this point has this behavior, go up and go down. So the local maximum, so minus 5 and 104 is the local maximum. And then this behavior is like this. It goes down first and then immediately goes up after that point. So this means 1 and minus 3 is the local minimum. So what I want to draw your attention to is that this is a level 1 problem according to the book. But if you compare, it is lengthy compared to the level 1 problems that you had in Math 1C or even the previous chapters. So you have to prepare yourself for this. Any questions? So essentially this is the essence of what I taught you so far about determining this. Okay, let me add something to it now, because that's also something you need to know. If we want to sketch the graph of this function, so what we do, so of course this number is a very bad number here, but it's very big. But anyway, so what we do, we need to understand what's going on. Scaling is nothing important here when we want to sketch the graph. So minus 5, so I don't know how to exaggerate, so it is minus 5. Let's assume that this is minus 5, and I don't know, this is 104, yes? And then the other, so here around this point, I have a horizontal tangent because the derivative is 0, but the point is a maximum point. So around this point, the graph should look like this. Yes? And then I have 1 and minus 3, so where is 1? So this is minus 5, so let me make this 1, 1. And minus 3 is actually very, very close. I mean, this is not very important. And then here the derivative is 0, and this function is minimal. So this means that it looks like this around that. And there are no other surprises for you. You can immediately realize what is going to happen. But let me ask you, do you think that this cut that happens on the y-axis is inevitable? Because if I want to take this one to this one, I have to cut both the y and the x-axis. But do you think that the cut for the y-axis, which is easy to understand, is above the x-axis or below the x-axis? The cut that happens for the y-axis is above this line or below this line? Yes? It is above, because if I put x equal to 0, I get 4. So this means the cut on the y-axis is exactly 4. Calculating the exact point of the cut on the x-axis is not always easy. Because if I want to know the cut on the x-axis, I have to put this equal to 0 and solve it. and the third degree equation is not easy to solve. But always the cut on the y direction is easy. You just put x equal to 0, yes? So when I put x equal to 0, it is 4. So this means that if this is 4, the cut is here. So I have to draw it a little bit more carefully, and then it goes down, and it goes forever up. So something like this. This was not in this question, I added, but this is part of your lesson. So you also need to be able to sketch the graph of the function, but this was not part of the solution. Not part of this problem. Okay, but how close is that to reality? I think this is a little bit of exaggeration if you also want to get a good feeling about what is going on. So let me just do it on GeoGebra. Okay, so here let us just type this in. So y is equal to x to the power of 3. And then I have plus 6x squared. And then I have minus 15x. And then plus 4. So this is what is happening, yes? Okay, so let us see. So now you see what is going on. Actually, you probably could expect such a scenario, yes? Because if I move it up, you see that this happens where? At 104, yes? So it's going up to 104. That's exactly what we predicted, okay? So, yeah, you can make it better, more beautiful, or make it clear. So by rescaling this, so you can click on this one, and then I always forget which rescaling is good here. Which one is good, do you think? Yeah, that one was horrible, yes? The other way around and make it more steeper, that's not beautiful even. So if I do that, then that is bad, it's worse. So I mean, flatter for my eyes is better. Okay, so let us make it flatter, and then at least you can understand what is going on by moving around, okay? Yeah, it's not very good probably. Or it might be you can start zooming out to see all the picture. Yes, now it's better. So that is the idea. So you start rescaling and then zooming out or zooming in appropriately to see the good picture of that. Is that clear? Okay, let me just ask you some questions in deviation. Do you think there is a... did I talk about inflection point here?
Yes.
No, not yet, yes? Okay, I did. For example, do you think that there is an inflection point for this function as well? Yeah, it seems so, yes, because for example, it should be around here, yes? Before that, the function is concave down. Apparently, after that, the function is concave up. Definitely, there is an inflection point for this function, but where is it? We can find. By the way, I realized that in GeoGebra, you can also find an inflection point by typing that, I think. Yes, inflection point. We can also find that. We can test the idea here. So inflection point, okay, inflection point of the polynomial. I don't know if it's working in that way. No, I have to type the polynomial in, but it will give you the inflection point. I didn't know about this feature before. Because if I want to find the extreme values, it is quite simple. You don't need to type anything. You just go here. Remember these things. You will need them in the national exam. So here, what do? You go to here and then extremum. This is probably the plural form of extreme. I don't know why this is written extremum. Is it the plural for extreme?
Yes.
Or it's a British English, I don't know. Anyway, you call that one and then you just click on it. And this will give you the extreme points. And the extreme points, you see one of them is -5 and 104, exactly what I got here on the board, and 1 and -4. I want you to know about these things because I told you in national exam, they intentionally design questions that you have to use the application. Otherwise, even myself cannot solve them. Yes?
This is -3.
Is it? So I made a mistake somewhere. Where is it? So that is good that you check. You see, this is always good. If I put 1 here, 1 plus 6 is 7. 7 plus, yes, that's my mistake. That's good. Thank you, GeoGebra. So we have to be thankful, yes. And then we write -4. So that is also -4. Yes, that's good always to check. Okay. I really urge you to practice your skills using GeoGebra because there are some odd features there that I don't like. Okay, so corrected that. Okay, let us go to another problem. Let us see which one is good to choose for solving today. Same problem, if you look here, but they are asking only about the local minimum point. But essentially this problem and that problem doesn't have any differences. Okay, this one was a good problem, but I solved for you when I was teaching. So if you have forgotten, you can go back and see that. That was exactly the example I used when I was teaching. Okay, I would say these kinds of questions that starts from this number are good questions. Okay, the following graph, be careful, this is not graph of the function. These are very common questions in Math 3C. So the graph of the original function we don't know. But someone has some function in head, that person differentiate the function, it becomes a new function, and that new function is being drawn here. So what you see is not the graph of the original function, is the graph of the derivative function. Okay? Now, for which value of x, f has an extreme value, a local extreme value? This is a good question. I intentionally start with this one because I want you to understand the idea in this simple example. Then there are more involved examples coming later. Okay, do you have any idea? So let me just try to copy more or less this picture on the board. Given us any number here, but according to what I see, yes, this is the picture I see. It is passing through 1 and minus. Okay, so that is also 1 and minus 1. Yes, so something like this. Okay, anyway, this is the graph of the derivative of a function. We don't have access to the graph of the original function. But the point is that we want to, by looking at this graph, we want to see for which value of x the original function has an extreme value. And then the second part, they are asking if that extreme point is a local minimum or a local maximum. Okay, how do you answer that question? Yes?
I'd say the extreme point is minus 1, 0.
No, minus 1, I agree with you. This is, no, this minus 1, okay, so 0, I'm saying that minus 1 is correct, but 0 part is not correct. And by the way, there is no way for us to know the y value. This I want you to understand. Do you have any questions up there? No? Okay, so how can we answer this? If you want to find a local minimum according to the recipe we just learned, what was the first step, do you remember? Differentiate the function. In the language of graphs, they have already differentiated it because they have differentiated it and given us the function f prime. The second step is to do what? Put f prime x equal to 0. I have to do the same thing here as well. The logic is the same. So I put f prime x equal to 0. In this case, I had to solve the equation, but in this case, I had to read it from the information given on the figure. Okay? I am asking you, by looking at the graph of this function, which is the derivative function, can you tell me at which point or points the derivative is 0? Don't look for horizontal tangents. Don't get confused. This is not the graph of the function. This is the graph of the derivative of the function. So where is the derivative is 0? Yes?
Then it crosses the x-axis.
Any function, whenever you want to see when the function is 0, you see where the cut is with the x-axis. The cut is minus 1. Is there any other cut? At least what we see, no. So this means that f prime of x equals to 0, it gives you what? Okay, tell me, is that understandable? So x is minus 1. So again, what do I have gained so far? You see, I am repeating the same kind of questions. This is the only candidate for either a local maximum point or a local minimum point or a terrace point. We don't know which one is it. But by looking back at the graph, we should be able to identify the nature of that point. Now, can you identify it for me? Yes? It's a local maximum. Why is that? Because let me just draw the table here for you and you can complete it here for me. X, F prime, and F. Yes? Let me try to tell you. So I put -1 here as I did in the previous example. I'm exactly doing the same thing in the previous problem, but sometimes I need to refer to the figure. If I ask you what is the derivative below this, you know it is 0. Okay, so now Buel, you told me -1 and 0. For me, is there any way to answer this question? I want you to understand right now. There is no way. There is no way for you to understand this number by the graph of the derivative. Okay, I will elaborate a little bit more on that. So this week, we have to live with it. This is our ignorance, yes? We cannot do that. But you need to know where the derivative is positive and where the derivative is negative. So this is my -1. So let me draw this border in my head. Before -1, this is the derivative. The graph of the derivative before -1 is higher than the x value, higher than the x-axis. So what does it mean? It means the derivative is positive or negative? Yeah. It's positive. Exactly what you said is correct. I'm just telling you how to have to understand. That is positive. And then immediately after -1, this is the derivative. And then the graph of the derivative, which is the y value, is below the x-axis. So this means the derivative is negative. Is that understandable? Because this is the derivative function. Yes? So this is negative. And then, as Melchior mentioned correctly, before that it is increasing. After that it is decreasing. So this point, -1 and the question mark, is the local maximum. And this is why, if you refer back to the question, they have asked only for x value, because there is no way for us to answer the question mark. Okay? And by the way, the reason is that there is no one function whose derivative is this graph. There are infinitely many functions whose derivative is this graph. Okay? For example, if I know the derivative of this function is this graph, if I shift it down, the derivative of this function will be the same thing, because shifting down and up means just adding a constant to it and its derivative becomes 0. So that is why there is no way for us to understand the height of the original graph. We need extra piece of information which is not provided in this problem. Is that clear? Yes or no? Okay. If I want to test your understanding now. Okay? Because I don't want to page the book, because the next time we'll reveal it. Now, can you draw a graph for the derivative, which by looking at the graph, you see that the original function has a terrace point? Is the question clear? Let me repeat. So here, there is a graph. You realize by this analysis that there is one point in the original graph which corresponds to a minimum. Now my question is that I give you the whiteboard pen and then I ask you to draw a graph and then convince me that graph, which is for the derivative, somehow corresponds to a terrace point in the original function. Let me everyone think, then I will ask you. So my question is this. I just draw the coordinate system for you. For example, I pick a point here for you, say 2. And I want you to draw a graph for the derivative of the function in a way that guarantees 2 corresponds to a terrace point on the original graph. First of all, tell me, is the question clear? So you want to draw any graph, any kind of, I want to tell me how the behavior of the curve for the derivative looks like around 2, so that it guarantees that the original graph has a terrace point corresponding to x value equals to 2. I hope that the question is clear. Yes, Will?
I suppose a parabola which minimum point is on the axis.
So what is your opinion?
The same.
Can you tell me why? Yes?
The reason that a terrace point.
So first of all, because you say that it's minimum or touch it.
Yeah.
Okay, so you mean something like this, you mean? This you mean? Something like this?
Yes.
Okay. Yeah, that's correct. But why is that correct? Yes, let me just give turns to people, yes?
Because we can see that
If this is f prime, assume that this is f prime. Now tell me why this is correct, what they said.
because we can see that before 2.
No, before going to that, you need one condition first. For example, do you think I can draw something like this? Do you agree with this one as well?
No.
Why not? So you need to tell me. That's one part of the story.
It's because first we have to put f prime as 0.
0. So it means, first of all, if I ask you what is f prime of 2, what is your answer? It is 0. Now you draw a table. So here is 2, here is f prime, here it is 0, here is f. Now, what is the sign of the derivative before that?
It's positive.
So this is your border. Immediately before that, you have this part of the curve. I don't know what happens there, I don't care. But at least immediately before the point, the curve is above the x-axis, so it is positive. So this is positive. Yes? And then, immediately after that, again the curve is
It's again positive.
positive. So this is a terrace point of which type? Of this type, yes? So it is very interesting. So it means that somewhere on this line, at which height I don't know, but I know at some point the curve is like this here. The original graph. Is that clear? So I don't know the height. It might happen here, it might happen there. I cannot have access to the height, but I know that if the derivative function looks like this around 2, the original function around 2 looks like that. Okay, now let me ask you another question. Can you draw a picture so it corresponds to another type of terrace point? Because you know that we have 2 types of terrace points. This type of terrace point is the increasing part, and this one should be decreasing point, yes?
A parabola whose max point is.
It was max point is that, yes? So that is clear. So now you understand more or less everything, yes? So because I hope that you agree that this point corresponds to a terrace point somewhere on this line. We don't know the height, but then the derivative is all negative, so it should be something like this above there. It's a very important connection. If you know this, by the way, I don't know, have you these kinds of questions in physics? Have you studied mechanics? Because you know that the first derivative of the position is velocity, and the second derivative of position is acceleration. So sometimes, I don't know, have you encountered these kinds of questions that you have the diagram for the velocity, you want to know something about the diagram of the acceleration, and vice versa. Yes? So these kind of things are actually very helpful when it comes to there. Okay, so now I think you will learn everything. So let me just page it and then ask your opinion about this. So there is another question. I think they really deserve some kind of higher level question. So let me spend time on this one. I want you to think about the problem first here. So again, look, be careful about, especially in the coming exam for this chapter, not the previous chapter that you are doing. So when I draw a diagram, there are 2 possibilities. Either I give you the function itself, or sometimes I give you the graph of the derivative of the function. Don't confuse them. So this is one of those cases that the graph of the derivative is given. For example, this is the graph of the velocity of a moving object. We want to know something about the graph of the position of that object. Or this is the graph of the acceleration of an object. We want to know the graph of the velocity of that object. Yes? That is the meaning of these kinds of questions if you want to think from a physical standpoint. Okay. Okay, just I want to wait for you. Please try to solve it. I mean, take a piece of paper and just write the numbers there so that you can check your understanding. Okay? Then I want to solve these level 3 problems with your help. I don't know. I haven't checked this one if that's a good idea. Might be that's also a good exercise. We will come back to it. Let us focus here. I give you 5 minutes, okay? Okay. So I try to actually sketch somehow more or less. Hopefully I haven't done something wrong, but you can just consider my graph. It is I hope that I haven't counted these grids wrongly. But let us go back to the board now and try to understand the problem. Okay. So I would say that it is a good practice if we start drawing the original graph. Okay? But the only thing that I want you to understand is that I will be able to qualitatively draw a good picture for the original graph, but I will not be able to fine-tune the height correctly because I can have all kinds of heights. So let us, for example, to understand it better, I draw another x-axis on top. Let me see, I don't know where should I start, but okay, so here. So assume that this is your x-axis. And now with my blue pen, I want to qualitatively draw the graph of the original function. So this is the graph, according to the problem, of this function, derivative. Okay. So hopefully you already know what are important points. Yes? So for example, these points that I have the cut with the x-axis are important. Yes? Okay. So these are candidates for local extreme points or terrace points. You already know actually that. So what this is? What is this? Here the derivative is 0. Yes? Before that, the graph of the derivative is below the x-axis, so it means the function is the derivative is negative. And then after that, immediately after that, the graph of the derivative is above the x-axis, so it means that the derivative is positive. So the derivative goes from negative to positive. So it means this is it's a minimum to positive, yes? So from negative to positive, so it is minimum. So it means that, for example, around this point up there, so let me just clean this because I don't know the height, so let me just clean that. But above this point, for the original graph, I will have this kind of behavior. So this kind of behavior for the derivative implies this kind of behavior around the same point, but for the original function. Yes? Now, let us look at this point. I hope that you can immediately tell me what type of point is that.
Maximum.
It's a maximum, because before that, the derivative is 0, first of all. The second, the left part is positive, the next one is negative. So it is positive and negative. So it is max point. So this means that here, I have, let me just draw them for the time being. I have this kind of behavior for the original graph. Okay. And now you already know what is happening for this one. What type of behavior you expect up there?
Terrace.
A terrace point of which type? Of decreasing part, because the derivative is always below. So it should be of this type. Yes? Okay. And then one of these things is here. So what type of point is that? before it is, first of all, the derivative is 0, but before that the derivative is negative, after that the derivative is positive. Negative, positive, which is minimum again. So that's also a minimum. So this is exactly what they are asking you in this question. Okay, so we actually answered this question. But let us try to understand it a little bit better. For example, can you tell me other points of importance for the graph here? For example, let me change my color. This is no longer part of the solution. Okay, so let me ask you, what is your opinion about this? This point for the derivative, we haven't studied that quite well yet, but you need to have a good understanding of what is going on. What is that point? Can you elaborate on that? But it is not a terrace point, because we already located the terrace points. The terrace point, the derivative should 0, so the graph of the function, of the derivative function should be tangent to x-axis. But this is not tangent, yes?
It's the inflection point because before that the derivative is increasing, after that it's decreasing.
So it means?
So, I mean, it's an inflection point because...
No, inflection point has nothing to do with the derivative.
No, well, I mean...
So let me ask you one question. If this point is 2, if this point is minus 2,
yeah.
Can you answer this question exactly for me? What is f double prime of minus 2? Do you know what is f double prime or not? No, so you haven't studied that. F double prime, okay, so let me just, don't bother, okay? Forget about it. I will come back to this later. Okay, so now if you want, you can glue these pictures together, assuming that the original function is continuous. By the way, it is continuous because there is a theorem that guarantees that if the function is differentiable, the function is also continuous. The function is differentiable because you see everywhere that you see the derivative exists. So it means that if you want, you should be able to glue them together. Yes? How can I glue them? So because this is minimum, this is maximum immediately occurring after that. So what do you expect? If this is minimum, this is maximum, it should be a little bit higher. So this becomes, this is your minimum. This should be happening a little bit higher. And what about this one? There is no way I put it up there. Because if I put it up there, it should go like this. It gives me another extreme point, which I don't have. So it means that this has to be below. But below than that, I don't know. Okay? Let me just draw that. And then I have this minimum occurring after that, something like this. So hopefully, somehow we convinced ourselves that this is the graph of the original function. The only weakness about this, the only deficiency here, we don't know exact height. So this is the graph of the original function. But I don't, by the way, I made a mistake. I should be able to draw it exactly on top of this. So this will happen here. This will go, this will go to a maximum. And then I have to come here somehow, and the terrace point occurs here. Yes? And then this minimum should be somewhere, for example, here. And then this becomes this. I mean, this is the behavior of my function. So you should expect something like this for the function. Yes?
You said the inflection point has nothing to do with derivatives?
Yes, it has. But it has something to do with the second derivative.
Okay, but I thought that...
But I want to tell, so if you want to tell me, you can say that f double prime of minus 2 is 0. Yes? Because at this point, we have a horizontal tangent. It means the derivative of this graph at minus 2 is 0. But this is already one derivative. The derivative of this becomes the second derivative. So we know that the second derivative is 0, and then you are right. The second derivative is 0 is a candidate for an inflection point. Yes.
But I thought that, what I thought was that basically the inflection point is where before that you can, it's...
No. That doesn't have anything with increasing, because this is an inflection point.
Yeah.
This is an inflection point.
Yeah, well,
And this is increasing.
yeah, exactly, but before that the derivative is increasing, right? because it's actually.
Yes, that's that the derivative of this one is increasing, which means that f double prime is positive.
Yeah, exactly.
Yes, exactly. Yes. But it doesn't have, again, this is second derivative.
Yeah, okay.
Okay, but now let us try to solve some level 3 problems. I want to wait for you because we have enough time. I would say that 5 minutes you think about this problem. These problems are algebraically very simple. They put it on level 3 problem because you have to have a deeper understanding of what is going on, not because it is algebraically harder. Because you need to think, okay? So I want to wait for you to solve this problem for me. A function is given to you. We want to find P and Q, and we have this information. By the way, it is a very, sorry for saying that, it is a ridiculous problem. Because it has nothing to do with what we have learned. I was mistaken, so this is not a good question. Because in principle, they can ask this question. I can give you this question in the coming exam. Because it has nothing to do with the material we learned in this chapter. But anyway, okay, let us jump it. It's not a good problem, we don't waste our time. But this is a good problem for the coming exam.
Like the next.
This is the coming Tuesday. Because I can ask this question on that exam. It has nothing to do with local maximum, local minimum, nothing. But let us try to solve that problem now. This has something to do with what you need to know here. Okay, I want to wait for you to solve me this. So even if your guess is correct, you will not be able to get any points. Okay, by the way, first of all, I want you to understand this is two different problems.
Yeah, exactly.
Okay, so first you solve the first part, it is finished, and then you go again back and solve the second part. Okay, because you cannot force both of them. It is clear if you have two local extreme points. It's not that clear, but I mean these are two problems. Okay, I want to hear from you. So, but let me write the equation here. Okay, what is the first step that you start for part A? So part A, the function is given to be what? X to the third, yes, ax squared, and then you have plus x. Yes, do you want to say something now? So what should I do?
You take the derivative.
Okay, the first derivative, yeah, I will take it. So I differentiate it once. It's 2ax plus 1. Okay. In the first part of the problem, you demand having two local extreme points. Okay, so how you can translate it to mathematical language?
You want to have two intersection points for the derivative in the x-axis.
And for this function.
For this.
Yes, okay, then how you, okay, that's, your understanding is correct, because to find the local extreme points, what I do, I put this equal to 0 to find the candidates. But when I do that, I know that I am facing a second degree equation, and I know from my previous studies for a second degree equation, I have three possibilities. Either there are no zeros, or there is 1 0, or there is at most, there are 2 zeros, okay? But according to the problem, if I do not have any zeros, it means that I do not have any candidates. If I do not have any candidates, then it means that I don't have them, yes? If I have exactly one value, then it means that I have one candidate. So there is no way, if it might be even fake, this one, but at least I have only one candidate, so I cannot have two local extreme points because I have only one candidate. So the only thing that happens is I have to force this equation to have 2 zeros. Forcing this equation to have 2 zeros, it means that the discriminant of this should be positive. So what is the discriminant of this function? So if I put this equal to 0 and try to solve it, if you understand it in that way better, you don't need to write all the equations, but let me just write it. You really don't need to write all the equation because what you care is just the discriminant. you have to only work with that one. Assume that you want to solve that equation. So it becomes minus 2a plus or minus the square root of this one to power 2. And then minus 4 times that one, which is 12, divided by 6. This is your x. Okay, you only care about this part. Because you don't want to find x, you want to force this equation to have 2 roots. So this means that 4a squared minus 12 should be strictly positive.
Why should it be minus 12?
What?
Should it be minus 12 in the
It's minus 12, yes.
Or shouldn't is not supposed to be?
No, minus 4a times c.
Okay, then I have my formula written correctly.
Yeah, so that is 4a squared minus 12 is greater than 0. Okay, then it means that this is why you see the algebra is extremely simple, but this needs you need a deeper understanding. Okay, but then how can I solve that one? This we already did, if you remember. So I move this to the other side, which is, and then I divide by 4, which is this one. Okay, I want to see how many of you remember. So what's the answer? A squared is supposed to be strictly greater than 3. So what's the answer? Think about. So of course it is clear that a is greater than a square root of 3. But is this the whole story? Yeah? Should be.
A is less than negative square root.
That is also acceptable. Yes? So a should also be, not should also be, either this one or that one. So if a is greater than a square root of 3, or a is less than minus a square root of 3, when you square it, it becomes bigger than 3. So this is acceptable. So that is the solution to the first point. So it means that if you want to do that, you have to choose a either greater than a square root of 3 or less than minus a square root of 3, but doesn't matter which one. Whatever you put here and draw it by GeoGebra, you will see that you have 2 extreme points. Is that clear?
Yeah.
Okay, now this problem is finished. I take the same function, but I want to answer the second question. So what should I do now?
You want to force it to only have one to meet the x-axis points.
Oh, show me everyone.
Yeah, because
Or no.
I want to have, by the way, I don't know in Swedish, when it is in English, so let f of x be this, where a is a constant, for which value of a, f of x has this in English, if I translated 1 terrace point.
Yeah.
Is that right?
Yeah. Yeah, exactly.
Okay, so 1 terrace point.
Isn't this just
Okay, but because you know that, in principle, if you have 1 terrace point, it is not inconsistent with having extreme points as well.
Yeah.
Okay? So this is why it needs a little bit of analysis. So is that translation correct? When you say 1 extreme point, it doesn't rule out that you have to force it, have it 1 terrace point without having local extreme points. That is my understanding at least. Is that right? Okay, but then how then you can elaborate then? So the function is this, x to the power of 3 plus ax squared plus x. We want to guarantee to have a terrace point, not to have guarantee to have, not to have extreme points, yes?
yeah, but in this
In this case, yes?
in this case, if you just want to find the terrace point, can't you just use the same strategy, but you want to find that for a power of 2 minus 12 is equal to 0 to find only one root.
So I put the derivative again. So the derivative is as before. So let me start from scratch. Assume that this problem is given from the beginning. Again, for the terrace point, you know that what happens? The derivative should be 0. Okay. Now the point is that one of these roots, there are either no roots, which is not the case, because then we don't have terrace point, because we don't have candidates, or we have one candidate and then if that is the case, we want to force that candidate to be a terrace point. Or we can have two candidates, then at least one of them should be a terrace point. Is that understanding this? My understanding correct? No, that's what I'm saying. At least this is the thing that we need to think, and if it is not possible, to rule out those possibilities. Yes?
Yeah, but in a parabola, is there more than one extreme point? Like in a parabola, you can't.
This is a parabola. This is the derivative. The derivative is a parabola.
Exactly. In this group, like you can't have any other extreme points here, right? Because you can only, if you wanted to.
Yeah, because that is good, but you need to tell me this. I mean, this is why, because might be this the question, they can ask you the same question, but to start with the by the degree 4 equation. This is why this is the analysis that you need to make. But that you are right, because you tell yourself that now the derivative is a parabola. By the way, what type of parabola is that? It's opening up. Okay? So then I will have this scenario. I don't care. Let me just draw the x-axis because I don't care about the y-axis. If this parabola is like this, then I don't have any hope for nothing. No terrace point, no extreme points. Okay? So this is not good. We have to rule this out. This is not going to happen. Either I have this scenario, which is good because we learned before, by the way, this corresponds to a terrace point. Or we have to have something like this. But then we lose our terrace point. Because for having a terrace point, the derivative should touch the x-axis. So even though, I don't know, but this is the way, because if you start with the 4th degree equation, then the derivative becomes a 3rd degree equation. This analysis becomes harder. Okay, so that is why I want you to understand that this is the only thing. This cannot happen, because if this happens, I do not have any terrace points. I will have 2 extreme points. So this is not good, so I need to have this one. So what does it mean? It means that I have to force this to touch the x-axis. Okay? It means I have to force this to have one single root. For having one single root, the discriminant should be 0. So this means that, okay, by this analysis, then you know what is A. What is A? So 4a squared is 12, a squared is 3. So what is A? Plus or minus square root of 3. Okay, so let us, by the way, check this with GeoGebra and then we are done, okay? Okay, by the way, you can use, I said forget about the inflection point. No, because if you use GeoGebra to find the inflection point, if that inflection point is a terrace point, it will provide it for you. So you can use this. I will test this as well. But let us say, for example, let me pick one of these numbers. For example, square root of 3, and put it into the function itself and ask GeoGebra to draw the graph. What we expect? We expect to have one single terrace point without having extreme points. So what type of function is that? It's very simple, yes? So it should be something like this, yes? Only. Because I have a terrace point without extreme points. So this is the prediction with the graph of the function. Okay? So let us check that. So I pick a square root of 3, for example. Then I have y is equal to x to the power of 3, and then I go down plus square root of 3, a square root of 3, and then times x, and then I have, no, times x squared, sorry, times, oh, it is under that, so I come out, and then x to the power of 2, and then I go down plus x. Okay? So are you ready? Let us see, yes, prediction was correct. So this is the graph of the function when a is the square root of 3.
Shouldn't you multiply the square root of 3 by all the 2?
No, I am not. I am drawing the graph.
Oh, right.
The function itself. This is the graph of the function itself, and the prediction was right. Because if you look at this graph, if you don't believe, I can zoom out a little bit. Of course. And we know that there are no other surprises for us. And then, by the way, do you think the terrace point? Okay, let me just teach you this one as well here for this graph. Assume that you want to ask GeoGebra to find the terrace point for you. By the way, what do you think the terrace point is? Is it happening at 0?
No.
I don't think so. Let us calculate. There is no terrace point, I don't think. Is there any terrace point? No. Is there any? Okay. But there is inflection point instruction, yes? So let me, by the way, this copy and pasting of this GeoGebra, I don't like it. Did you find a way? Is Control C standard in Windows or not? It is on Mac. Okay, so Control C. Okay, and then I want to write inflection. Oh, what happened? Inflection point, and then I need to type my polynomial. Hopefully it will work. Control V. Yet it's worked. Okay, and then I press enter.
You lost an X.
No, X is also here. Oh, okay. Now let me just put X back. I don't know why I lost X. I really don't know what to do. So X to the power of 3. Now it is up there still. X to the power of 3. Yes, it is good. So this is your terrace point. Of course, GeoGebra gives you the inflection point, but in this case, the inflection point is terrace point. So you can use this instruction to find your terrace point. And these coordinates are the coordinates of this terrace point. So if I insist to do it analytically, how can you find these numbers? So how should I do that? I need to put, for example, a square root of 3 here. So this becomes this number. And then I need to solve this equation. Because I chose, for this graph, I chose a to be positive, the square root of 3. Yes?
Can you also take a on the other function?
Here?
To be square, no,
Here?
yeah.
No.
Square root of 3 on the...
No, because, okay, I can put it here. I actually put it there, and then I have to differentiate to find the terrace point. So instead of putting it here and then differentiate it again, I put it in the derivative, and let me solve that. So this becomes minus 2 square root of 3 plus or minus a square root of what happens here, 0. And then divided by 2 times 3, which is 6. So the answer is minus a square root of 3 over 3. This is the exact value that I get. Yes. Let me check this exact value is correct.
I might just confuse my number, but I find it a bit strange that both plus and minus square root of 3 is like we found 2 answers. Like, so what? Is there no difference if you put negative or positive?
No, it is a difference. The graph, I will tell you. So let me just confirm that. Divided by 3. And that is exactly I calculated. You see? This minus 0.58, this number that GeoGebra find using this syntax is exactly the one that I calculated here. What is you're asking is, so what is the take on from this? It tells you that for forcing this type of function to have one single terrace point, we have 2 options. Either I have to choose a to b square root of 3, or I have to choose a to b minus a square root of 3. Of course, I will get 2 different functions, but both of them. If I want to draw that, for example, I can go back here, and then I ask GeoGebra to take it minus. Yes? And then I go and draw it. And you see, the terrace point is not that one, but can you predict what is the value of terrace point now?
0.
Because here it becomes minus 2, then it becomes positive 2. So this becomes positive square root of 3 over 3. So it should be positive 0.58. So let us check that. So I go back here, and I changed it to minus sign, and then go all the way out, and that is my prediction. So that's correct. It's 0.58. So this is the way that you need to learn mathematics. Just so when you solve a problem, try to see it from different perspectives and use GeoGebra in a correct way so that you know how to solve the problem. Any questions? Okay, so next time you will have the exam on Wednesday, so I will not teach you on Tuesday. In case you have any questions, you ask me, and then we have the exam on Wednesday. So let me just end the